All right, so 3.11 is hyperbolic functions. Now, the question arises is, where does a hyperbolic function come from? All right. If you notice it, it comes from the idea that we have a certain odd and even combination of these exponential functions, e to the x and e to the minus x. The fact that those combinations, they arise frequently in mathematics. So we then decide to give the odd and even combination of those exponential functions in a special name, all right? And you can see here, they say they also, they say in many ways, they analogous to the trigonometric functions. And they say they have the same relationship to the hyperbola that the trigonometric function have to the circle. So we came up with such beautiful name called hyperbolic function, all right? And individually, we just call each of those functions. So for example, we have hyperbolic sine, hyperbolic cosine, hyperbolic tan, hyperbolic sec, hyperbolic cot, and so on, all right? The difference is that you notice that there's an h there to know that we're talking of hyperbolic. So please make sure you know what the difference is. So if I say sine, I'm not going to put an h, but if you see I put sine h, I'm talking about hyperbolic function, all right? And these definitions, guys, very important. You need to know this. So this is a definition of hyperbolic function. So hyperbolic sine, you can see there's e to the x minus e to the power minus x over 2. All right. Okay, that's a nice question. Someone said, can you call hyperbolic sine change? I've heard that many times, but if you're speaking to another person who understands what you're saying, then it's fine. But if you the first time you say to someone that is not familiar with hyperbolic function, they might not know what you're talking about at all. They might be so confused, and they might interpret it as you're trying to say sine. All right. Yes, I've actually heard of those in the past. All right, people saying change, cosh, tange, and so on. All right. And then take note the difference between hyperbolic sine and cos. There's a minus for cos, yes, a plus in between the e to the x and e to the minus x. Obviously, hyperbolic tan is hyperbolic sine of hyperbolic cos, and hyperbolic cosec is just the reciprocal of hyperbolic sine, and so on. All right, so make sure you study this table because this definition, especially this first two, is very important. You're going to need it most of the time. All right. I see there's someone raised their hand. Does anyone have a question?
So I was going to, just say on that example of calling it shine and kosh and so on. When I did university maths about 20 odd years ago, we were taught to use those definitions: shine, kosh, than, etc.
Yes, yes. Like I said, it's very allowed. So it is correct for you to say Sharon's kosh. But for the purpose of me lecturing you, I'm going to use the word hyperbolic sine, just so that someone who is not familiar might because someone who is not familiar with what we're saying might think I'm talking of the sine and the cos instead of the hyperbolic version. So the fact that I keep stressing on hyperbolic sine, so someone will know I'm talking of sine, all right? But yes,
Okay.
you're more than welcome to say sines, cos, tan, and so on. All right.
Okay, thanks.
All right. Some identities. So when it comes to identity, notice that the sine and hyperbolic sine, they both odd functions. So you can see there, hyperbolic sine of minus x is just minus hyperbolic sine of x. So it shows you that the hyperbolic sine function is an odd function. Hyperbolic cos function is an even function. You can see there, because hyperbolic cos of minus x gives you hyperbolic cos of x. It means it is an even function, right? Now look at this identity here. So you see there's a little difference from what you know. From trig, for the normal trig function, we say sine squared plus cos squared equals to 1. But for hyperbolic, we say cos squared minus sine squared equals to 1, right? So please make sure that you understand the differences. And obviously, to get this one here, you just need to divide all through by hyperbolic cos, all right? get that 1 minus hyperbolic tan squared is equals to hyperbolic x squared. Okay, and then obviously hyperbolic sine of x plus y is similar to the normal trig version. And then hyperbolic cos of x plus y, notice it here is a plus instead of a minus. All right, and to understand the relationship between the trig functions and hyperbolic functions, what's the relationship between them, you can quickly read on something called Osborne's rule. All right, so Osborne's rule. So Osborne gave us a good relationship. So Osborne gave us a good relationship between the normal trig function and the hyperbolic function. And specifically, he mentioned that when you see a product of sign, you change the sign from positive to negative or from negative to positive. For example, if I say cos of x plus y, you notice it's going to be a minus because it's a hyperbolic version. You see product of sign, you have to add the minus there, become positive. You now see why we have a positive there. All right, we're using Osborne's rule. All right, good practice identities. Let's look at example 1. So typically in the assessment, I will say prove this identity. And as usual, you need to show that the left-hand side simplifies to the right-hand side or the right-hand side simplifies to the left-hand side. Let's see for A what we can do. My best advice is when I ask you to prove hyperbolic identities, go back to the definition of the hyperbolic function. For example, hyperbolic cos, you know, is e to the power x plus e to the power minus x over 2. And then hyperbolic sine is just e to the power x minus e to the power minus x over 2. Square those, look for the difference. Notice it, you're going to get terms that cancel out to each other. For example, this cancels with that. This cancels with this. Take note there's a minus in between there. That's why it cancels out. You end up with 2 minus minus 2, which becomes 4 over 4, as you end up with 1. So you see, therefore, left-hand side is equal to right-hand side. Right. Now, to prove part B, there's no need to go back to the definition of the hyperbolic function. If you choose to go all the way to the definition, it's fine. Your final answer will still be correct. But since you've already proven this first part, you can just go ahead and say, okay, if I divide all through, so if I divide this first identity there all through by hyperbolic cos squared, it works. I get the second identity. So that's what they're showing us here. That starting with part A, if you divide all through by hyperbolic cos squared, you just end up with 1 over hyperbolic cos squared, which is this side you end up with hyperbolic sec squared, and then you have 1 minus hyperbolic tan squared. All right, and left hand side again equals to right hand side. Now for derivative of hyperbolic function, if I ask you to find the derivative of hyperbolic sine, obviously you're going to go back to the definition. So you see it's very important to know the definition. So d dx of e to the x minus e to the minus over 2, if you differentiate, look at this looks exactly like hyperbolic cos x. So we come to a conclusion that derivative of hyperbolic sine is equals to hyperbolic cos. And as a table of summary, please make sure, very important, you know this table. Very, 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 very important. You must know this table. All right. If you differentiate sine, obviously you get cos. If you differentiate hyperbolic cos, you have hyperbolic sine, hyperbolic tan, you get hyperbolic sec squared. I think this three kinds of look like your normal trig, except for the fact that for a normal trig, if you differentiate cos, you have minus sine. But for hyperbolic, is you differentiate hyperbolic cos is just hyperbolic sine. So please don't get confused, because most of you tend to treat hyperbolic function as your regular trig function, which it doesn't work. All right, so you must know what the difference is. Also have the derivative hyperbolic cosec, hyperbolic sec, and hyperbolic cot. So please make sure you know this and know the signs. Please make sure you remember what the signs are. All right. Let's see now how to apply chain rule to some hyperbolic derivatives. So if I ask you the derivative with respect to x of hyperbolic cos of root of x, chain rule says you start by differentiating the other function, which is this function there. It's just the hyperbolic cos. If you differentiate hyperbolic cos, what do you get? You get this, hyperbolic sine. And then you need to differentiate the inner function, which is this root of x. If you differentiate root of x, you get what? You get 1 over 2 root x, and there you go. You've applied your chain rule. Find the numerical value of the following. Guys, this example is a must. You must also know this kind of small examples. They're very easy to evaluate, and usually I like asking this for my multiple choice. If I ask you for hyperbolic sine of ln of 4, I'm asking for the numerical value. So obviously you go to the definition of hyperbolic sine. So you get what? You get e to the ln of 4 minus e to the minus ln of 4 over 2. Simplify that, you end up with this. All right. And if I ask you for hyperbolic cos of hyperbolic sine of 0, start with this one inside here. Do hyperbolic sine of 0. The fact that if it's multiple choice, I know most of you probably just punch in your calculators, but if it's a free response question, you have to show me working. So you have to use that definition of the hyperbolic function. So get used to making use of the definition of the hyperbolic function. All right. So if you get the result of hyperbolic sine of 0, you plug it into hyperbolic cos, you end up with 1. All right. So go practice and make sure you can get those answers. All right, here you need to differentiate. Again, you can see for both A and B, we need to use chain rule. Chain rule, you start by differentiating the outer function. So you differentiate ln of hyperbolic cos, so you get 1 over hyperbolic cos of 2x. And then you have to differentiate the inner function, which is hyperbolic cos. You get hyperbolic sine. Hyperbolic sine divided by hyperbolic cos, you can see why we have hyperbolic tan. And then it's not yet over. You need to differentiate the 2x itself. All right. So you differentiate 2x, you get 2. That's why we have 2 there outside. All right. The same rule applies for B. You start by differentiating hyperbolic sine. You see here we have hyperbolic cos of 4x. You move one step in, you differentiate hyperbolic cos now. You see we have hyperbolic sine, this one here. And then move one step in again, you differentiate the 4x, and you see we have 4 outside. All right. So please, chain rule is very, very important. Make sure you always apply chain rule when differentiating composition of functions. And that's basically for hyperbolic functions. So do all these examples, do the examples that you see in the dot, and do some at the back of your textbook, and you should be very comfortable with any hyperbolic question that I ask you. All right.